Buongiorno a tutti e benvenuti all'Astromeeting. Oggi è uno Astromeeting un po' particolare perché abbiamo l'onore di ascoltare il vincitore della prima edizione del premio Capocci, premio che abbiamo istituito qui a Capodimonte grazie alla donazione di un erede di Capocci proprio destinata ad articoli scientifici di punta nell'ambito di studi del sistema solare, e quest'anno il vincitore è Paolo Simonetti, che viene da Trieste. Ha perfezionato i suoi studi di astronomia a Trieste sotto la supervisione di Francesca Martinucci prima e poi di Vladi e Fulvio successivamente, specializzandosi quindi in tematiche relative al sistema solare. E poi il vincitore di un assegno di ricerca cofinanziato dall'INAF, dedicato proprio a studiare la tematica attraverso i nuovi metodi numerici delle atmosfere planetarie. In particolare la tematica molto interessante di questa discrepanza, no? Che c'è tra la temperatura di Marte, la superficie di Marte legata al fenomeno di insolazione e la compatibilità con la presenza che sappiamo esserci state da circa 4 miliardi di anni fa. Quindi l'articolo che è stato premiato ha portato un contributo originale a questo argomento e sembrerebbe avere anche un impatto molto interessante per studi sulla future missioni e sull'abitabilità del pianeta.
Grazie, faccio un inglese o in italiano? We can switch to English and thank you for the invitation and good morning everyone. And in this presentation I will talk about the role of seasonal thaws in explaining, solving, possibly the mass painters and paradox. The content of this presentation is based on a paper that we recently published in APJ and the press, and that we hope it will be out soon. So let's start by talking about the science stories behind this work. And in particular, we start by taking a small, let's say, historical review and the topic of larger mass. Some travelers in the 1800s identified some negative features on the surface of Mars for possible standing bodies of water at the surface.
Speak a bit like louder because they said they cannot hear you very well.
Okay. Maybe sit down just in front of the microphone.
I'm sorry to interrupt. Is it possible to adjust the audio for people that is in remote connection? Because looks like we are not hearing well.
Try again. Can you hear us now?
It's very metallic and with some echo.
Questo che si risponde.
Bravo.
Ok, no?
No, è sempre uguale in realtà.
No, non lo so dove si risolverà, perché siamo già
speravo che mi succedesse la legge. Grazie.
Adesso sentite meglio?
Sì, ora sì.
Sentite meglio adesso?
Sì, sì.
Io sì.
Perfetto, allora sì, abbiamo cambiato microfono.
Grazie.
Niente, scusa. Lo metto più vicino così sicuramente.
Grazie mille.
Niente.
Okay, sorry for the inconvenience, but the mic is not that good on this laptop. So we were talking about the topic of water on Mars. Basically, what I was saying is that during the 1800s, some astronomers misidentified low albedo features in the surface of Mars for standing bodies of water on the surface of the planet. And this sparked a little bit of interest in this topic and in the possible presence of a biosphere on the planet. However, this lasted only few decades, because already at the beginning of the 20th century, spectroscopists found little to no traces of water in the atmosphere of the planet, and also they theorized that the atmosphere was very thin, actually, and unable to support a biosphere. The first pictures taken during the 60s by interplanetary space probes confirmed this later vision as a geologically dead and dry body. However, just under a decade later, more high-resolution pictures taken at the surface from the orbit showed the presence of these, let's say, morphological traces in the form of ancient riverbeds and valley networks that hinted at the possibility of the presence of water in the past, in the ancient past of the planet. These kind of valley networks are not the only morphological clue on the possible presence of water on the planet. For example, there is a common elevation in the delta-like fluvial deposits on the surface, especially on the rim of the large northern basin of the planet Mars, that seems to identify a sort of shoreline. There are also petrological clues on the presence of water in the form of fluvial conglomerates. Conglomerates are a type of rock formed by small pebbles that have been cementified together by salt inclusions. And also chemical clues on the presence of water in the form of water-altered minerals. So there is a piling amount of evidence that in the deep past of Mars, some water was present on the surface of the planet. However, there is a problem, because most stellar evolutionary models are in accord in saying that stars brighten up during the main sequence phase. And so, if we go into the past of our solar system, we can suppose that the sun was fainter. Since most of these traces of water has been found on terrain that has been dated to 4 to 3 gigayears ago, at that age, the sun was 20 to 25% less luminous than today. And this is a problem because even today the planet is cold. It has an average temperature on the surface of 210 kelvins. And so it seems difficult to explain how, in the deep past, it was able to host liquid water on the surface. And this is the origin of the name of this paradox, faint young sun paradox. In the decades since the first photos of valley networks, several possible solutions have been proposed in order to solve this apparent paradox. And these solutions can be largely, let's say, grouped in 3 sets. The solutions that focus on increasing the greenhouse effect of the planet in the past, the solutions that tries to explain this, the presence of water as caused by transient heat-injecting phenomena, and solutions based on seasonal thaws on the surface. These 3 groups cater to possible, let's say, early Mars climatologies. A warm and wet Mars, in the case of the increased greenhouse case, or a cold and icy Mars that transiently was heated up by some event in the other 2 cases. All these solutions have been investigated using climate models of a variety of complexity levels, from zero-dimensional single column models that give as output the surface temperature for the entire planet, to one-dimensional seasonal latitudinal models that basically take the planet and subdivide in a number of latitudinal zones and then go to evolve the temperature at its latitude, or 3D general circulation models that find the surface temperature on a grid of latitudinal and longitudinal pockets. So we now can go a little bit deeper in these solutions and why the problem is still, let's say, unsolved, or at least not satisfactorily solved up to this day. And we can start by talking about the solutions that focus on an increased greenhouse effect in the past of the planet. The most straightforward way to, let's say, suppose that a planet is hotter is to suppose an increased greenhouse effect. And the most straightforward way to increase the greenhouse effect is to increase the amount of greenhouse gas in the atmosphere of the planet. So we can suppose that in the past, Mars had a thicker CO2 atmosphere than today. CO2 is a good candidate as a greenhouse gas because it is abundant in the outgassed fluid, like during volcanic eruption, for example. It is more or less chemically stable in the sense that it can remain in the atmosphere of Mars for a long time scale, and it cannot be blown away by the solar wind in meaningful quantities. And as such, it is a good candidate for an accumulated, let's say, greenhouse gas in the atmosphere of the planet. In fact, if you increase the amount of surface pressure, of CO2 surface pressure, you can actually decrease the amount of effective solar flux needed to support a certain temperature on the surface, as you can see in the plot. Basically, for a 5 to 6 bar atmosphere, you can support a 273 Kelvin average temperature at the surface, even with a solar flux which is 15% less than today. However, there is a problem. And the problem is that CO2 is also an efficient Rayleigh scatterer. This means that if you accumulate a larger and larger amounts of CO2 in the atmosphere becomes more and more reflective, and as such, the amount of absorbed radiation decreases. At a certain threshold value, this anti-greenhouse effect becomes dominant, and as such, what happens is that for higher surface pressures, actually the effective solar flux to support a certain temperature increases. So CO2 is a good candidate, but it has a limit in the amount of greenhouse effect that it can contribute to the atmosphere of the planet. And the amount that it can contribute is not sufficient alone. A possible way to solve this problem is to suppose the presence of a second greenhouse gas, like, for example, hydrogen. Hydrogen is another important component of outgassed fluids, and together with CO2 is an efficient greenhouse gas because of the so-called collisional-induced absorption bands in the infrared. In fact, if you add more or less a 3% concentration of hydrogen in the atmosphere of the early Mars, you can, as you can see in the plot, you can warm up the planet above the 273 Kelvin threshold for an atmosphere with a surface pressure between 1 and 3 bars. This is a good thing because from the distribution of the crater sizes on the surface of Mars, there are, let's say, clues that the maximum surface pressure that could have been present during the Noachian era was below more or less 3 bars. So we are interested in solutions that can produce a warm climate with a relatively low surface pressure. However, also in this case, we have a problem because differently from CO2, hydrogen readily escapes from the atmosphere of Mars, and as such, you need a very high flux of hydrogen from the surface in order to support a 3% concentration of this gas in the atmosphere of the early Mars. And you should do this for like hundreds of millions of years. In order to support this level of hydrogen concentration, you need or a flux which is order of magnitudes higher than the flux currently present on Earth of hydrogen. So this is a problem. If we instead consider the, let's say, solutions that takes into consideration heat injecting phenomena, we can start talking about asteroid impacts. An asteroid 200 kilometers in size can vaporize more or less 10 meters of global equivalent layer of water on the surface of Mars, which is a lot. And if it happens like several times during the history of the planet, you can, in theory, excavate these riverbeds and leave these traces that you see today. However, this solution also has some problems because the post-impact precipitation simulations doesn't match basically the position of most of the valley networks. In particular, the deluge-like precipitation that you expect after an asteroid impact as a minimum at the latitude where you have the maximum number of valley networks. So this solution is not particularly good either, or at least have some issues that are still unsolved. Another possible solution is to take into consideration volcanic eruptions. Volcanic eruptions put a lot of sulfur-based compounds like SO2 and H2S in the atmosphere of the planet, and these are very effective greenhouse gases. In fact, calculation shows that with concentration around 10,000 to 10,000 ppm of these two gases, you can actually heat up the planet above the 273 Kelvin threshold, and so deglaciate the planet. But if you take into consideration the photochemical transformation of this molecule in the atmosphere of the early Mars, you find that SO2 and H2S are subject to a rapid recombination driven by ultraviolet radiation that produces basically solid sulfur in the form of finely grained particulate and sulfuric acid droplets. Both of these particulates are very reflective, and as such, what happens is that after a volcanic eruption, in just a matter of few years, the greenhouse effect of these gases disappear, and in their place you have an anti-greenhouse effect from the particulate, and as such, the final effect is to cool down the planet rather than heating it up. Seasonal thaws are instead taken into consideration because mainly of two things. The first thing is that Mars doesn't have a large moon that is able to stabilize the axial tilt of the planet, and as such, the axial tilt is subject to chaotic variation on a relatively short time scale. What you expect is that over a 1 gigayear time scale, you expect to have extraction of the axial tilt up to 60 or even above 60 degrees. Also, the orbit of Mars is perturbed by Jupiter, which causes large variation in the eccentricity of the orbit of the planet. Both large obliquities and large eccentricities causes a stronger seasonality on the planet, which means basically that the minimum temperature that you reach during the winter and the maximum temperature that you reach during the summer can be very large at a certain latitude. As such, someone considered this a possible solution of this early Mars Finkel Sun paradox, in the sense that you can obtain at specific latitudes under some combination of orbital and planetary parameters, you can obtain temperatures that are locally above 273 Kelvin. So the planet on average is colder, but at a certain latitude you have, let's say, a milder climate that can produce these, let's say, water runoffs. This kind of hypothesis has been investigated using both 1D and 3D models for generally very low pressures, like pressures that are comparable to those of current Mars. And we asked ourselves if ourselves if this kind of solution could have been applied also to an early Mars with a little bit thicker atmosphere. And in order to investigate this possible solution, we used two tools that we developed in Trieste, that are the EOS and the ESTM models. EOS is a GPU-based vertical radiative transfer model, which is basically a model that propagates a beam of light through a simulated atmospheric column, and for each simulated layer, calculates the amount of light that is reflected, absorbed, and so on and so forth. This model is derived from two publicly available and validated codes that are called EOS and Helioscale. What I've done during my PhD was basically take these two codes, modify them in order to use them to study rocky planet atmospheres like CO2-dominated atmospheres and nitrogen-dominated atmospheres, and to validate these codes. And the way we use this radiative transfer model obtained by this combining these two codes is to produce lookup tables of two important radiative quantities that are needed for climate simulations. These quantities are the outgoing wave radiation as a function of the surface temperature, and the top of atmosphere albedo as a function of the surface temperature, the surface albedo, and the zenith angle of the incoming stellar light. These lookup tables are then used by the actual climate model, which is called ESTM, or Earth-like Surface Temperature Model. ESTM is a 1D model, a seasonal-latitudinal energy balance model that basically evolves the temperature of each latitudinal band over time, finding as such the, let's say, the seasonal evolution of temperature at each latitude. The equation that the model integrates is the one that is in this slide, and basically you have a time evolution term, a meridional transport term, because several different latitudinal bands can exchange heat, and the vertical transport terms, I, S, and A, which are calculated by the radiative transfer model. This model also includes some simplified surface processes, like, for example, the growth of the ice coverage when the temperature is particularly low, and basically a simplified parameterization of the effect of clouds in the form of modification of the top of atmosphere albedo term and the outgoing wave radiation term. In order to apply this model to these models to the study of Mars, we have to introduce some other modifications to them. In particular, the first thing that we needed to introduce was the, let's say, the topography of Mars. Now, Mars has this striking topographical dichotomy between the northern lowlands and the southern highlands. And obviously, this dichotomy has strong impact on the climatology of the planet, because due to a simple effect of the atmospheric gas rate, the lowlands are on average a little bit warmer than the islands. This effect is not seen today with the thin atmosphere that Mars has now, but if you put 1 bar, 2 bars, 3 bars of CO2, this effect becomes more important. Since this dichotomy is, let's say, mostly a latitudinal feature, it's not only a latitudinal feature, but is mostly a latitudinal feature, we were able to introduce it in our model, which is a latitudinal model. We cannot resolve the longitude of the plane. And basically what we have done was to take the molar altimetry map and to bring it in latitude in order to obtain a latitudinal altitude profile. We then added the oceans, and in particular we tested 3 possible, let's say, models for the oceans of Mars. The first model was basically a no-ocean model, in which we supposed that the amount of water on Mars was very low, and as such no extended water, let's say, water surface was present in the past. The other two models was to consider a 150-meter global equivalent layer ocean and a 550-meter global equivalent layer ocean. In these two latter cases, we found the possible shoreline on the altimetry map and then used it to calculate the latitudinal fraction of ocean at basically at each latitude. What we obtain is that basically the planet is divided into a northern hemisphere, which is more or less covered in water, and a southern hemisphere, which is more or less dry, except for the Hellas Basin. Using, including the effects of ocean and altimetry in our model, we obtained some, let's say, deep changes in the structure of the surface temperature of the plane. In the plot on the left, you can see the temperature, a temperature map as a function of latitude and the orbital phase, which is the standard output of our model, for a 0-meter level altitude. So basically, it's a uniform altitude map. In the plot on the right, instead, is the altimetry corrected temperature map. And as you can see, the, let's say, an altimetric dichotomy of the planet translates into a temperature dichotomy. And also, in this case, we were able to identify, for example, in this specific, let's say, simulation, that on the southern pole, we have some CO2 condensation, which is another thing that we checked in our model. In particular, these two maps have been calculated for the same obliquity of 45 degrees, the same eccentricity, 0.09, which is more or less the model value, and 1 bar CO2 plus CH4 atmosphere. Another thing that we wanted to include was some model for the, some modelization of the clouds. As I said before, our model cannot actually, let's say, model clouds from first principles, but we can use a simplified parameterizations of the radiative effect that clouds have on the planet. So, for example, increasing the albedo and decreasing the autoinoculate radiation, so producing a little bit of, let's say, greenhouse effect themselves. In this work, we tested two possible sets of parameters for clouds. A first set that was calibrated on the water clouds of Earth in terms of albedo and OLR forcing, so OLR decreasing, and another set of parameters that was calibrated on CO2 ice clouds calculated by the Forgetta 2013 model. In both cases, we calibrated our clouds in order to obtain basically a sort of, let's say, in order to obtain the final effect of the clouds, because as I'm saying, our cloud model is only parameterized, it's not calculated from first principle. What we have done at this point was to explore the planetary parameter space, which means basically that we tested a lot, we produced a lot of climate simulations, let's say, using the fact that this climate model is very fast and doesn't require a lot of CPU hours to produce a single simulation, we basically varied a series of parameters in order to produce a vast array of climate simulation in the order of 10,000 different climate simulations. From each climate simulation, for each combination of input parameters, we derived maybe let's say, three variables that we were interested in. The maximum temperature in each simulation, which identifies if a thaw can occur or not. The minimum temperature, that is important to determine if there is or there isn't a CO2 surface condensation. So if the atmosphere condenses at the surface during the winter, let's say, or not, and the duration of these thaws. So what we basically did was to take one by one the combination of the parameters that I showed in the previous slide. For each combination, we ran a single simulation of our kind of model, which we called a case. And from each case, we extracted some variables, in particular, the maximum temperature, the minimum temperature, and the duration of the thaws heat horizon. And then we used these quantities to build these parameter space maps of these quantities as a function of the initial parameters that we input in the model at the beginning. And these are the results that we have found. First of all, we started investigating the effects, the combined effects of surface pressure and obliquity on the maximum temperature. We were interested in this in order to identify the, let's say, the combinations of these two parameters that were able to give rise to this seasonal thaws. And the maps that you see are maps of maximum temperature, so they basically report the maximum temperature as a function of these two variables. The yellow and red curves identify the region of the parameter space for which you have thaws of pure water, because the yellow line identified the 273 isotherms, and thaws of brine, which is basically salt-saturated water. And the second isotherm is at 252. The hatched region identifies the combination of parameters that causes the atmosphere to condense at the surface, so causes the CO2 component of the atmosphere to condense. The three panels identify three different models for the atmosphere: an atmosphere without methane, an atmosphere with 0.1% of methane, and an atmosphere with a 1% concentration of methane. As you can see, we actually found that those are possible in all atmospheric models, so with all, let's say, concentration of methane in the atmosphere, even around 2 bars, which is important because, as I said, 2 to 3 bars is a sort of upper limit for the surface pressure of the Mars. But we need a very high, let's say, humidity in order to obtain this. If we put a little bit of methane in the atmosphere, the region of the parameter space that allows for those become increasingly larger, and this is good because obviously this means that there are more combinations that can give rise to these, let's say, water runoffs on the surface of the planet. We then investigated the effect of eccentricity, and we found that eccentricity alone is actually not very important, at least not for atmospheres with a pressure above 1 bar. For pressure below 1 bar, the effect of eccentricity can give, like an high eccentricity can produce these seasonal thaws, but in this case, the problem is that the atmosphere generally condenses for this kind of models. And so basically, you have thaws, but you have also, let's say, a partial atmospheric collapse at the surface. We repeated the experiment also for various values of the land albedo, and we found an interesting thing, which is, for example, that in the model with a 1% methane concentration, the surface albedo is actually not a very important, let's say, variable. In particular, you can obtain seasonal thaws even when half of the southern islands are covered in ice, because basically a 0.41 land albedo is equivalent to say that half of the surface has the same albedo as today, and half of the surface has an albedo of 0.6, which is the typical albedo for ice, for example. Another variable that we investigated is the cloud cover fraction. This is a very important variable because actually the cloud modeling is not good, let's say. In our model, we use a parameterized clouds, so they are not even physical clouds, but even models that include physical clouds, physical cloud modeling inside themselves, has serious problem in finding, let's say, a good correspondence with the physical reality. So there is a lot of uncertainty in cloud modeling, and as we found, cloud modeling at least in the form of the cloud cover fraction, has a strong influence on the surface temperature and on the possibility of having or not these thaws. The only good news is that if you put, again, something in the atmosphere, a 1% meeting in the atmosphere, you can have these thaws even for very low cloud coverage level. So even if clouds are not particularly, let's say, potent as a greenhouse contributors, they can still, let's say, this atmosphere can still produce seasonal thaws. The effect of ocean fraction is instead a little bit more difficult to explain, in the sense that yes, oceans are low albedo features. It is a low albedo feature on the surface of a planet, and so if you cover part of the planet with an ocean, you are actually decreasing the average albedo of the surface of the planet. This alone eats up a little bit the planet. However, an ocean can glaciate, obviously, if the temperature is too low. But the ocean has also another effect, because if you increase the amount of surface which is covered in water, you can expect to have higher and higher levels of water vapor in the air. So if you have extended oceans, for example, you can expect to have a relatively high level of relative humidity in the air. And this is important because water vapor is actually a very efficient greenhouse gas. In fact, what we have found is that in the model with 0% ocean coverage, which we basically set the relative humidity to 0, the atmosphere is not able to, let's say, hold up itself, in the sense that for most cases the atmosphere condenses during the winter because the greenhouse effect is too low. Instead, if we put a little bit of water on the surface and a little bit of water in the atmosphere of the planet, like 20% relative humidity, which is equivalent to the relative humidity you can find in an Earth desert, in this case, you can have a stable atmosphere and also, let's say, thaws. Thaws, you can have thaws also in the case with 0% water vapor, but in that case, the problem was that the atmosphere tended to condense. We also explored the effect of the argument of perihelion, because if you have a relatively high eccentricity and a relatively high obliquity, changing the argument of perihelion causes this, let's say, seasonality effect to combine in different ways. And what we have found is that in limiting cases, so for example, in a case where the surface pressure is not particularly high and you have an open thing, so it's a limiting case in the sense that below this pressure, you find only, let's say, cases in which the atmosphere condenses. What happens is that if you change the argument of perihelion, you can actually stabilize the atmosphere. In non-limiting cases, so for example, when the surface pressure is 2 bar, 3 bars, and so on and so forth, what happens is that a different value, the argument of perihelion, can double the duration of the thaw phases from around 20 to 25% of the Martian year to 50–60% of the Martian year. Talking about the duration of phases, we were interested in checking if these thaws are, let's say, real or not, in the sense that when we did our first investigation, we only checked if the surface of the planet at a certain point in time, at a certain latitude, was above 273 kelvins. But we didn't check at the beginning the duration of this, let's say, warm period. When we checked it, we found that actually when thaw begins, it usually lasts for at least 15% of the Martian year, and the average duration of the thaw phase is around 30% of the Martian year. So these thaws can actually provide a meaningful amount of liquid water for the, let's say, excavation process of the networks. Also, above a certain pressure threshold, we found basically a continuously warm and wet condition. So basically, we fallen into the warm and wet Mars case. We were then interested in particular to see those who were possible, not in a random point on the surface of Mars, but specifically in the southern hemisphere, because most of the valley networks are on the southern hemisphere. So basically, we checked for a variety of atmospheric composition, surface pressures, and obliquity, if what were the regions in the southern hemisphere in which you can actually have these seasonal thaws. As you can see, we basically need a 1%, at least some methane in the atmosphere, at least a 1% concentration of methane in the atmosphere in order to deglaciate the southern islands, because obviously, since they are islands, they, let's say, they have an average temperature which is lower than the temperature at the 0 meter altitude. So, to conclude, we studied the possibility of seasonal thaws on the early Mars for a wide range of parameters in order to identify what are the conditions that can actually give rise to these thaws. We were in particular interested in studying cases with a low amount of non-CO2 gases. So we were interested in having an atmosphere mostly composed of CO2, and to have, let's say, these thaws with surface pressure below, let's say, 3 to 2 bars, because at higher pressures we have problems with other traces like the crater size distribution. What we have found is that methane or other greenhouse gases are actually not strictly needed to obtain thaws, but if you do not put a little bit of methane, you obtain thaws only on the northern lowlands, which are on average warmer. As little as 0.1% concentration of methane can instead produce thaws also on the southern islands, but you need a pressure which is a little bit higher than 2 to 3 bars. Instead, if you put a 1% concentration of methane, you can have thaws both in the south and in the north for relatively low surface pressures. Then we investigated the effects of eccentricity, obliquity, and the argument of perihelion, finding that they have an impact, an important impact on the maximum temperature. In fact, the maximum temperature can change up to 50 degrees, up to 50 kelvins for a 1 to 2 bar atmosphere. Then we found that those are possible in the southern hemisphere, even if half of the southern hemisphere is covered in ice. So even if the albedo of the planet is higher than the Then we found that if a melting occurs, it generally lasts at least 15% of the Martian year, which means that we have no fake, let's say, thaws, not ultra-brief thaws, and these thaws can actually contribute some water to the excavation process. And then we found that we actually need a little bit of water vapor in the atmosphere in order to stabilize the atmosphere, because, as I said, water vapor is a strong greenhouse gas, and it contributes to the solution of the problem, in a sense. Finally, if we consider drying runoffs instead of pure water runoffs, the main, let's say, problem becomes the CO2 concentration, the CO2 condensation at the surface of the planet. Because if we consider drying runoffs, actually a vast part of the parameter space that we explore can give rise to this kind of melting events. There are just a couple of ways that there are a lot of ways in which this work can be expanded, but just a couple of these came to my mind. One is to test other atmospheric mixtures, like, for example, photochemically produced gases, because photochemistry not only destroys greenhouse gas, but also creates other molecular species that absorb in the infrared. We can improve the cloud model, which is a very important thing to do, and also we should calculate the actual amount of water that can be melted these thaws because we made estimate on the duration of thaws, if thaws occurred or not, but we didn't actually calculate the amount of water produced. But it is a little bit difficult to do with an energy balance model, simplified model like our own. It would require 3D general situation models to do this. And with this, I conclude my presentation.